So it's great to see you all today. Today we are going to finish the ecosystems unit by finishing the phosphorus cycle, the sulfur cycle. We're going to review the water cycle, which we learned earlier in the year, and then we're going to have a few summary remarks. So let's get going. Comparing the phosphorus cycle to some of the other cycles, the first thing you're going to notice here is that phosphorus has no gaseous phase. There are no phosphorus gases in the atmosphere. All phosphates in ecosystems ultimately derive from minerals, and before humans were around, these minerals slowly dissolved and then were picked up by ecosystems where they cycled internally within the ecosystem. And in this diagram, it shows two separate ecological systems that are cycling. A terrestrial ecosystem over here and a marine or aquatic, and you can think of both fresh and saltwater ecosystems, only shown here in this river system. Once phosphate gets into organisms don't really like to let it go very much, and it doesn't travel easily in the soil, so it stays put and it just keeps cycling and cycling around. Within marine ecosystems, some of the dissolved phosphates precipitate as compounds, especially in deep sediments, and then you have the formation of phosphate rocks, which eventually get uplifted and then eroded back into the living ecosystem. But the big idea in the phosphorus cycle is that most of it stays cycling internally in these ecosystems. So what are the effects of human beings on the phosphorus cycle? Well, it is primarily the addition of large amounts of phosphorus in the form of phosphate to aquatic ecosystems. And you say, so why is that a problem? Well, that's a problem because surface water generally has very low concentrations of phosphates, because phosphate compounds commonly precipitate as insoluble minerals. As a result, phosphate is often a limiting factor for plant growth, particularly plankton, and especially in freshwater ecosystems. And if you add phosphate to freshwater ecosystems, you get what's called an algal bloom. You can see that, just go down to the tidal basin or the reflecting pool in the middle of summer, and they are this bright green color. Those are all algae that have grown because of all the phosphate in that water. Let's move on to the sulfur cycle. In the sulfur cycle, all the sulfate in ecosystems ultimately derives from minerals, the same as phosphate. Normally, there is no gaseous phase, but you will see here there is a gaseous phase because humans have created it. And actually, that's not completely true. There is very low levels of gaseous organic sulfur-containing compounds that are in the atmosphere. Sulfur-containing compounds therefore cycle internally, which is shown here. So organisms pick them up, they stay in the ecosystem, and the organisms die or they shed waste, and that's recycled by the decomposer organisms, and the sulfur stays cycling internally. As I said earlier, gaseous sulfur normally occurs in low quantities, and its natural state is volatilized organic compounds created by certain aquatic bacteria. Most sulfur cycles ecologically through the ecosystems, but humans have put large quantities of gaseous sulfur oxides into the atmosphere. How? By burning fossil fuels, by refining fossil fuels, and by processing various ores. Sulfur oxides, it turns out, are a problem because things such as SO2 are highly toxic, especially to the respiratory system. In addition, sulfur oxide in the atmosphere gets converted into sulfuric acid when it dissolves in water, and this causes acid rain or acid deposition, as it's more commonly called these days. And we'll study that a little later in the semester. Finally, I want to talk about the hydrological cycle. We studied it earlier in the year, and I'm not going to review it right now for you, but one thing you should do is remember all the processes: precipitation, infiltration or percolation, runoff, groundwater flow, evaporation, transpiration, condensation, and vapor transport. And there are certain words for areas where water pools, such as surface water, groundwater, and aquifers. And aquifers are a type of groundwater. So hopefully you'll remember that. Thinking a little bit more about the water cycle than we did earlier, one of the things that we can now point out is that the hydrologic cycle renews water quality, and it does it in two ways. One is the percolation through the soil combined with microbial decomposition and physical sequestration causes purification of toxins in water. Further, The sun effectively distills water by evaporating it. So water is constantly being purified by this natural process in the water cycle. The second thing is that the water cycle provides all terrestrial life, including humans, with fresh water, which is absolutely necessary. If there weren't a constant source of fresh water, life would never have left the ocean. These are two huge ecosystem services provided by the ecosphere. And the asterisk there is just to remind you that if you doubt that these are valuable, all you have to do is look at the profits of the water industry, of the modern day water industry, to see how economically important fresh water is. How have humans affected the water cycle? Well, we've withdrawn huge amounts of fresh water from aquifers, underground reservoirs, and this has caused problems all over the place. And when we get to water pollution, I'll talk a little bit about that. By clearing vegetation and draining swamps and altering all sorts of ecosystems and hardening cities, we have changed the ratio of water that percolates into the soil versus runs off. And in fact, what we've done in general is sped up runoff. And this means that less water is retained. And when you retain less water on land, it means everything's going to be less productive. I just put buffaloes and beavers in the slide because they are two examples of organisms which were once abundant on the North American continent, now are relatively rare, although beavers are making a great comeback. And they play a big effect on retaining water in terrestrial ecosystems. So retention of water is big. We have drained so many wetlands, and aside from the fact that wetlands retain water so well, they also, if you get rid of them, they have the effect of increasing flooding, because wetlands act as sponges and they absorb a huge amount of flood water. They act as a buffer, and we'll talk more about that later on. So now I want to say a few words about matter cycles in general. First of all, when we think about energy, organisms or life itself needs a constant new supply of energy. If that sun weren't coming in all the time, life would cease immediately. In contrast, nutrients are constantly recycled through the environment. An old nitrogen ion and waste is recycled to a plant and eventually ends up back in our body. One nitrogen atom is as good as another as far as an organism is concerned, and matter is continually recycled and reused. Heterotrophs obtain sufficient nutrients as long as their food isn't scarce. In contrast, plants, as we learned in this unit, compete with each other for nutrients. So it's very different to be a heterotroph and getting nutrients and an autotroph and trying to get nutrients. These cycles are also driven by biological processes, not just physical and chemical processes. And so these incredibly huge geologic processes are primarily, in many ways, biological processes. And this means that biology has an effect on the geology of the planet. And that's an interesting thing to think about. Finally, the matter cycles themselves provide a model for how humans might want to live. How do they do that? Well, they show us that ecosystems try to hold on to their nutrients by recycling them. They don't throw things away to be lost forever from the ecosystem. From the ecosystem's point of view, that nitrogen needs to stay in there. Same with phosphate. Humans would do well to look at natural ecosystems and think about matter cycling when they build their economic systems. Think of all the materials we throw away and make them so that they can't be recovered again. So, to review this unit, I'm not going to review all the rules. That's left for you to do. What I will say is the laws of ecology allow us to start to think about ecosystems, how they're organized, and gain some level of understanding, especially about how they are similar, how they are dissimilar, and also about how humans are affecting local and planetary ecology. And by understanding these rules, they will also suggest ways for humans to minimize harmful effects on ecosystems. Ecology is an incredibly complex subject, and that's partially because there are so many moving parts, and partially because organisms have free will, and partially because they're based on historical contingency. In other words, what happened in the past matters to what we see today. And so we will probably never be able to understand ecosystems in the same way we understand physical systems, such as, let's say, the movement of the planets and asteroids and comets, in the solar system. So that's probably not a goal, but there is much to learn about ecosystems, and that is an exciting area of research for the future. Understanding the rules we have set out here will allow you to start to make sense of environmental issues and ecological issues, especially those you encounter in the future as you become voting citizens, as you become economic citizens, and as you become people who make the policy that will determine the course of the future after you are gone. In the next unit, what we're going to look at is the scale of human disruption of ecosystems and the scale of human disruption to matter cycles. And then we're going to look at some of the consequences of that as well. So I hope you have found the ecosystem unit interesting. And until next time, study hard.